Hello and welcome to the Spatial Structures Movers and Shakers interview series as we look ahead to the IASS Annual Symposium and Spatial Structures Conference taking place at the University of Surrey in August 2021. My name is Mark Richardson and today I'm joined by Ruy Pauletti, who is an Associate Professor at the Polytechnic School at the University of São Paulo. Ruy is also a member of the Editorial Boards of the Journal of the ISS and of the International Journal of Space Structures. Ruy has published more than 140 papers in total, with personal research interests, including the numerical analysis of cable and membrane structures. Ruy, thanks very much for taking the time to join us today.
Hello, Mark. It's a pleasure to be here.
Thank you, Ruy. Well, it's a real pleasure to have you on the Movers and Shakers interview series. We start by asking our guests about lockdown and the period of lockdown. I understand that's been a challenging period for you in Brazil, but maybe you could tell us more with regards to how it's been for you.
Yeah, it's have been a very difficult time around here in these last days. The number of casualties are rising in many cities. And the states went or are just going into emergency status, which is just before lockdown. Brazil is a federation of states, but with a strong central government, and this central government is mismanaging the answer to the pandemic so far. Luckily, most states of Brazil, such as São Paulo state, they are acting more consciously. São Paulo is producing a vaccine which is being distributed nationwide, and this is practically the only vaccine we have by now, because the central government refused to buy the vaccines abroad by the end of last year. Rio de Janeiro will locally produce AstraZeneca Oxford vaccine, but it will take some time before it reaches industrial scale. So right now we have vaccinated about 20% of the country. We have a population of 210 million people. So sadly, the pandemic will still get worse in the next days. But today I just read the good news that São Paulo state is starting to test a new vaccine. And if positive, the tests are positive, they will start large-scale production of this third vaccine by next July. So this is great news.
Yeah, it's a very challenging situation across the globe, and we've heard some very interesting opinions from different guests across all parts of the world. So thank you very much for sharing your views on things in Brazil, Ruy. We also look at the start of our interviews with respect to the career journeys and career paths of our guests. Maybe you could tell us a bit more about your own career journey, Ruy.
Okay. Well, I graduated in civil engineering by the Federal University of Rio Grande do Sul, which is the southernmost state in Brazil. It was then in 1984, I went to Padua in Italy, where I got involved in the design of experimental thermonuclear reactors, the RFX machine, under the supervision of Professor Bernard Schroeffler. I got very enthusiastic on the subject. And when I returned to Brazil, I worked for the Brazilian Navy and for a large engineering consulting company on the design and components for nuclear power plants. Soon I engaged the University of São Paulo, initially working at the Physics Institute, where I have been responsible for the mechanical design of a new tokamak reactor. And I defended my Doctor of Science thesis at the Polytechnic Institute, specifically on the structural design of this type of machines. And I also spent some time at Oak Ridge National Laboratory at the USA, solving some problems they had with their mechanical design of a new tokamak machine there. But then when the design of these fusion machines were complete, and they are used for a decade or 2 decades, so I should either move abroad again to engage on other fusion reactor designs or to change my research field. I couldn't wait 20 years to design other reactors. So by that time, I was already interested in the shape finding problem. Initially, because I had made the shape finding of some electromagnetic coils, bending free electromagnetic coils. But then I realized that very few people were studying cable and membrane structures in Brazil. That was in the middle of the 90s. So I decided to reorient my research to that field. In 2002, I was so involved in the field that I promoted to this first Latin American Symposium on Spatial Structures, which happened in Brazil, in São Paulo. And Frei Otto was our main speaker at that time. It was the first and only time that Frei Otto visited Brazil. Then I presented my habilitation thesis on the design and analysis of thought structures in 2003. And I became associate professor at the Polytechnic School at the University of São Paulo. And by 2004, I got involved with IASS. And in 2014, I have been the chair of the IASS Symposium in Brasilia, the iconic city where we have many inspiration now buildings by Oscar Niemeyer. And then I'm got fully involved with thought structures, cable and membranes.
Fantastic. Thank you very much, Ruy. And maybe you could tell us a little bit more about a research paper or a project you are currently working on.
Okay, I'm still interested in the numerical analysis of membranes, especially considering membrane wrinkling and the pneumatic stiffness. I have a recent paper on engineering structures about that. And on the subject, I have collaborations with Professor Sigrid Adriansen, Professor Slade Gelin, Professor Romuald Tarchevsky, and with a very bright student of Sigrid, Oleg Niewiarowski, who studied these wrinkling problems in membranes. I'm also finishing an extension to the natural force density methods, which is a shape finding extension to the renowned force density methods developed by Linklitz. So in 2006, I presented this extension for membranes. It's not the only proposed method, but it's a nice one. And now more recently, I extended it to 3D. And it's also a collaboration with Vinicius Arcaro, a colleague of mine from Unicamp. And I'm also working with student Marcio Sartorelli in a new program for the analysis of membranes. I had this in-house program called SATS. And now we are developing BATS, which is perform the same functions of design and analysis of membranes, but in rhino grasshopper environment. And it's becoming a very interesting, though academic program. I also got other interests in parametric design. I had this former student, Isabel Moreira. With her, we have developed a patent of a specific 3D printed parametric node for grid shells. So besides of that, using flexible formworks like membranes for concrete shells, a collaboration with my colleague Leila Meneghetti and my student Murilo Soto. So basically, this is what I'm involved with right now.
Thank you, Ruy. It sounds very exciting. It sounds like there's a good number of things going on there. So thank you very much for sharing that. Well, we're now going to move on to the middle section of our interview, which is entitled Your Space, Your Structure. So I will hand over the presentation to Ruy, who'll be presenting for a period of time on a spatial structures topic of personal interest to him. So over to you, Ruy.
So today I'd like to talk a little about thought structures, to give some basic concepts on that, some practical examples, and some learning by making activities that we developed mostly at the Polytechnic Institute of São Paulo University. So thought structures encompass a broad range of structures. We could mention suspension bridge, the sails of a traditional windmill, pneumatic toys, or the roofs of large stadiums covered with membranes. Thought structures are light structures in the sense that their self-weight is usually much smaller than the payloads they carry. In the sense they are potentially very environmental friendly because of small material consumption. Along the years, the weight of the structures per square meter has dropped drastically, and by the time of the Industrial Revolution, this weight were of the magnitude of a typical design wind load. Not the everyday wind load, but the strong wind load that the structure might experience during its lifespan. And with cable and membrane structures, this weight can be considerably lower than the wind load. So that changes the game because the foundations of the structure, instead of being compressed, they are under traction, and they can they must prevent the structure to fly away with the wind. Thought structures are also flexible in the sense that a stiff structure such as a beam does not change drastically the shape when loading varies. On the other hand, a flexible structure such as a cable can drastically change its shape when the loading pattern varies. Because of that, thought structures in general has to comply to funicular shapes, that is, those shapes that equilibrate a set of loadings without bending. In fact, each load pattern is associated to a family of funicular shapes. So here, this set of concentrated loads generate this family of polygonal arches and cables, and distributed loads generate continuous curved arches and cables. And in general, cables equilibrate transversal loads precisely by adjusting its curvature. Likewise, cable nets and membranes, they have to comply to single or double curvature surfaces. Usually, a pneumatic structure will comply to a synclastic surface. And pneumatic structures, nevertheless, can be synclastic, anticlastic, or single curvature. And they might present regions of these three conditions. On the other hand, self-stressed membranes are always anticlastic or flat. That's because in the initial geometry, they don't have necessarily a transversal load. This double curvature nature of most membrane and cable net structures brings the problem of planification. A single curvature surface can be flattened without distortion of length, area, or angles. However, while double curvature surface always undergoes distortion due to flattening. It's the problem of the map of the Earth, right? This almost a sphere. When it's planified, we have, like in Mercator projection, very large distortions of the areas as we get close to the poles, areas and length. A way to reduce this error is to split the surface into gores. And the more segments we have, the less will be the error. but nevertheless, there's always an intrinsic planification error for double curvature surfaces. Another aspect very relevant to thought structures is that they are characterized by geometric stiffness. So if we remember from basic mechanics, the frequency, let's take, for example, a spring mass system, and the frequency of this spring mass system goes with the square root of K over M, where M is the mass and K is the stiffness of the system. So the higher the frequency, the stiffer the structure is. Likewise, for a vibrating string, its frequencies, it has infinite frequencies, now goes with the square of T over R over M, where T is the traction on this string and L is the span. Now, we see that this ratio T over R plays the part of stiffness, and it's called geometric stiffness because we can show it is a reluctance of the system to change a given geometry. And you will see also that it doesn't depends on the material, it depends on the traction level. The more tighten is the string, the higher is the frequency, the higher is the stiffness. So this is what most essentially characterize thought structures like cables and membranes. All of this brings about a very peculiar design process where we start from an architectural orientation and we have an integrated design and analysis process where we have to perform a shape finding from some initial guess of this geometry to a final viable shape. Then we have to mind about splitting the surface into pieces, gores, and then to planify these pieces to produce from flat fabric. And then we have to perform load analysis, usually nonlinear structural analysis because of the high stiffness and large displacements of the system. And only iterating this process sometimes we can talk finally about design solution. So here I will present some cases like the membrane roof of the Memorial dos Povos of Belém do Pará. It's an interesting and not so large saddle structure. Here is the initial guess for the geometry. And after some iterations of shape finding, we get this saddle viable shape. Then we perform wind analysis, basically. Here, displacements for a lateral wind are kind of exaggerated but for 20 meters here, we have 40 centimeters displacement, which is very large. It would be very large for a stiff structure. Then we have the patterning and the flattening, and here we have assembled scale model. The assembling of this structure took only one day, and we needed only a hydraulic jack on this main stay here to apply the loads. By controlling the shape and the load at this stay, we knew that all the loads were correct. This is another example. In fact, the first case of a structure fully designed by computers in Brazil. It was in 2003. It's a very large structure. From side to side, it's 70 meters, only 2 poles. And here again, we have these fabric patterns. Here I have one example of learning by making. So we use this as a case for paper models with students, graduate students in this case. And here, the assembling of the structure, it was also very quick. And it was a kind of a show for the community. It was a church. So the community of the church, they followed with large anxiety to get the structure completed. and the riggers plays kind of a show for them. So it was very remarkable, the precision of all the details. It was very surprising for us. We had never achieved such quality before. This is another example, the open market in Goiânia, where the challenge was a very restricted budget that we had to get solutions for that. And a challenge was that it was two large membranes on a circular avenue. So we came up with these modules here in white. They are standard. The others are to absorb the curvature. Here we have a satellite view of these two very large membranes. And here I have, again, students assembling a scale model of this structure in front of Polytechnic School in São Paulo. So we assembled this model like 2 years in a row before changing to other models. Another interesting structure is SEMPES in Rio de Janeiro. Here, the challenge is that we had these very slender metal arches, which are stabilized by the membrane themselves. And still in Rio de Janeiro, on the top of Urca hill, we have these interesting membranes. I acted as a consultant to both of them. And this one in the front, if we look at the arch, here we have a very sturdy arch because of very high wind loads that we have. And it is very segmented because we should bring everything to the top by the cable car that goes up to the Urca hill. This is another interesting structure in Rio de Janeiro, the Olympic golf field. And this is a pneumatic dome to cover the ground of a new nuclear power plant in Brazil. It's still being constructed, but this dome was used to the impermeabilization work at the beginning of the construction. And we studied here the effect of the sliding of the reinforcement cables, how it affected the wrinkling patterns, and of course the load distributions on the border of this large cable dome. So we can see that depending of if the cables are adherent or are sliding, the loads are vary, and the wrinkling regions are also different. It's not easy to propose pneumatic structures as academic exercise, but sometimes we propose that this is the dodecoid. It is a pneumatic toy composed of two dodecahedra linked by 20 cables. So these are the numeric, a physical stiff model, the numerical modeling of the toy. Here we are producing it. And here we are playing with the toy in front of the Polytechnic Institute. So somebody should be inside, and at this moment it was me inside of the toy. Well, these models, they are becoming kind of expensive. So I started to reduce them to sculptures. So this one was proposed in Princeton in 2016. It is a Costa surface, a famous kind of surface in topology. and it is stretched by this bar, so it is a bending active structure. So we followed more or less the same process of designing, of shape finding, then finding the patterns, planification, and the production of the sculpture. These connections were 3D printed to have good precision. So here we have this sculpture displayed at Princeton in 2016 and at Hamburg at the IASS 2017. Again, this is another exercise, another sculpture in São Paulo. The Cusped Exiled. So we have only one pattern. Here they are being cut, assembled, and we put some lights and become an interesting lamp. This is in 2018, just before the pandemic. Nanoper surface, it was in Padua, where I studied soon after graduation. So these are the patterns, very intriguing patterns, in fact, and this is the shape that they produced. It took only 2 afternoons for the whole exercise in this case. It was a very challenging design. And that's it. This is a very recent structure inaugurated this year in Vitória, which is a state close to Rio de Janeiro. So this is the day of the inauguration of this structure. It's 10,000 square meters, designed by Nelson Fiedler, and I acted as a consultant to this structure here. So with this, I think I come to the end of my presentation on thought structures.
Roy, thanks so much for taking us through your presentation there. There was a wonderful number of examples of a very interesting and a really diverse mix of structures. I really enjoyed it. Thank you very much for that.
Yeah, it was my pleasure.
Thank you. We now move on to the section of the interview which looks towards the future of spatial structures. And a key theme of the 2021 conference is inspiring the next generation. What advice would you offer to aspiring engineers or architects looking to enter the field of spatial structures?
Yes, Mark, I believe there are still many current issues on membranes and bending active, and parametric design related to this kind of structures, all spatial structure systems. Pneumatics, tensigrids, origamis, deployable structures. I believe they will blossom in the next years. The combination of traditional and new materials, geopolymers, high performance concrete, glass, carbon fibers, bamboo, and wood, combination with 3D printing, artificial intelligence, neural networks, deep learning, digital twins, robots, drones, parametric design, the Internet of Things. They are setting the foundations of a revolution in the field of spatial structures. I think we have very exciting times ahead.
Great. That was a great answer, Roy. And when you put it in those terms, you realize what an exciting field it is actually, and how exciting it is that the future of spatial structures has and the space to evolve. So thank you for that answer. Building on that, what do you think are the most pressing challenges in the field of spatial structures, particularly with respect to current global challenges?
Yes, this type of structure has low consumption of material, and they have potentially a low environmental footprint. They are quick to assemble, and they produce less waste. They can be produced with environmentally friendly materials. So they certainly will play an important part on the answers to many global challenges. like environmental challenges, health challenges, social challenges of today and the future. They can be used as temporary or permanent structures. They can be used for humanitarian relief or to space exploration and perhaps even the colonization of Mars. So I think they will play a very relevant role. They are playing and they will play in the future a very relevant role.
Absolutely, yeah, very poignant answer there, Ruy. Well, Ruy, we've reached the end of the interview, but thank you very much for your time today and your insight into the world of structures. A quick reminder to the people watching this episode, registration for the 2021 conference is now open. Please head to the conference website for full details and information. And if you've enjoyed this video or indeed any of the videos in the Movers and Shakers interview series, please remember to like, share and comment. All of your views are very much welcome. Ruy, as I said, it was a pleasure to interview you today. Fantastic insight into your world of work. And hopefully as we move closer to the 2021 conference, we can catch up with you again. But for now, thank you very much.
Thank you. Looking forward to IASS 2021.
Okay, Ruy, all the best and speak to you soon.